Okay, is my screen visible?
Yes,
So, I mean, this chapter on triangles, we have already seen similarity of triangle. We have already studied it before, right? This will mostly focus
yes,
on similarity of triangle, and then you'll have multiple different shapes to work with. Say a quadrilateral, you can have a parallelogram, a rectangle, right? Then you'll have some questions that relates similarity, and then you'll also have some relation between similarity and area. So area is something. So I think we have done it in brief as well previously. The relation between similarity and area, right? Have we studied it?
yes, sir.
Yeah. So that also, I mean, level remains the same. I mean, concept remains the same. Level of questions changes a bit. Okay. So that is the only difference. You'll find most of the concepts already familiar to you, but yeah, most of the proofs I think we'll need to look at how to prove certain things, right? So you're already familiar with triangles and many of their properties, right? We have studied congruence of triangles. Congruence of triangles means two triangles or say two figures are exactly the same, right? So that is what we mean by congruence in terms of their shape, size, anything, right? So
Yes,
two figures are said to be congruent if they have the same shape and the same size. Now in this chapter we shall study about those figures which have the same shape but not necessarily the same size. Same shape. So there are two things, shape and size. Right? When we talk about shape, we are generalizing something. Say for example circle. So anything that has a shape like this is a circle, right? But size is changing, right? Circles are increasing in size. That we characterize by a parameter called radius, right? So shape means this thing. Say for example circle. So it is a shape. Size means use a parameter and then use that to see whether it is larger or smaller, right? Similarly square.
yes,
So these are all squares. So they are having the same shape, but their sizes are changing, right? So here you'll study about figures that have the same shape, but they are of different size, right? And they are known as similar figures,
yes,
right? So if there are two figures, so there can be a question to, I mean, it can be a viva question or a conceptual question to differentiate between congruency and similarity, right? So you can say two figures are said to be congruent if they have the same shape and the same size, whereas two figures are said to be similar if they have the same shape but they are of different size, right? Can or cannot, I mean, they can be of the same size or cannot be of the same size as well, because you know that if two figures are congruent they are also similar,
yes,
right? So two figures having the same shape and not necessarily, so that is why this is very important, not necessarily, so it can be but there's no condition that they should have the same size, so they can have different sizes as well. Okay, so they are called similar figures. In particular, we shall discuss about the similarity of triangles and apply this knowledge in giving a simple proof of Pythagoras theorem learned earlier. So see, do you know any application of similarity of triangle?
so similarities.
Yeah.
So,
Is there any application of using similarity? I mean, why are we studying this chapter on similarity of triangles?
so is it like equal to congruence?
No. Similarity is a bit different from congruency.
Okay. So it's like if they are similar or not.
Yeah. So, I mean, what is a real life application of studying that? If you don't have any application of that, whatever you are studying, what is the point of studying it?
So we can compare things easily.
Yeah, we can compare it easily. And it is mostly used for measurement. Right? For example, you can see this. So you need to find, you need to find the distance or say radius of the moon. Okay, or say distance from the moon. So you should know one of the parameters. So what you can do is, say you are standing here, right? So you can draw a figure like this. Right. So say this is the moon. Right. This is the point and this is distance. Right.
Yes.
This is where you are standing. This is the moon. And you want to find this distance.
Yes.
Right. So what you can do, you can draw this figure and then you know already your angle of inclination. Right. So you know the angle of inclination. So if you have any line in between, if you draw any line in between like this, right, so that is closer to you. Right. So this distance you are already aware of.
The landing the moon.
Yeah. Right. So you are already aware of this distance and you already know this distance. Right. So from the property of similarity, what you can say is this divided by this is equal to this divided by this. Right.
Yes.
So this is one way. Another way, you can also apply trigonometry. If you know this distance, you can then apply trigonometry. Right. And then another way is, say, if this is the moon, right? So you can draw two lines like this. So this will become the diameter of this moon. Right. So this is the diameter of the moon. Then again you do the same thing. So this is something that you have to know. So one thing you have to know. So if you know the diameter, you can compute this. If you know this, you can compute this. So this is one application of similarity.
Yes.
Okay. This is one of the application wherein you apply similarity of triangles. Then comes this concept of similar figures. So similar figures are figures that have the same shape. Right, for example, these are all similar figures. Right, so this is a similar figure. So this is an example of circle, which is a similar figure. Right, this is an example of square, which is again a similar figure. A triangle, which is a similar figure. And then, can you say whether this is a similar figure or not?
Sir, yes.
How?
Because they look like they are the same, but the first one is just normal.
They look the same, but say if it was a bit like this, only a slight change of 1 degree at this point, then also it would look the same. Right. So then it becomes difficult. So for example, all these figures, it was pretty simple. For example, circle is straightforward. Square, say if the length is slightly, say, increases by say 0.1 meter. Right. So say slight increase. So visually it would be challenging to see that difference. Right. And then we can say that these are similar. right? So we don't need anything visual, we need something mathematical that we can use to define whether two figures are similar or not, right? So when do we say that they have the same shape but they are of different size, right? So that definition is needed, and before that definition, yeah, go
So
ahead.
the ratio of sides or the angle should be the same.
Yeah, so there are two conditions, not or, it should be and, right? So there are two criteria. So before that, you should understand that all congruent figures are similar, whereas all similar figures are not congruent,
Yes.
right? So congruent means they are the same. So if you have a triangle, another triangle, if you draw the same triangle, so it will be exactly the same. So if these two triangles are exactly the same, they are congruent, right? But if they are congruent, that means they are similar as well, because they have the same shape and they may have the same size or different size,
Yeah.
right? So that means it is similar. But all similar triangles are not congruent. For example, these two triangles are similar, right? But are they congruent?
No, sir.
No, because they have uh, different size. The criteria for congruency is they should have the same shape and size. Here they have same shape, but they are of different size. Okay, this is one thing. Now, how do we define similarity? Similarity is defined by two criterias. The first criteria is same angle,
Yes.
right? The other criteria is sides are proportional. Sides are proportional. By sides are proportional, I mean we have an example to see. Say for example you have this image, right? So you clicked an image and then you try to print it using different papers, right? So these are three different papers on which you have clicked this image. Okay, are these similar?
Yes, sir.
They are similar, right? Because they have the same shape but they are of different size,
Yeah.
right? Now if you look at these two figures, right? So if you notice any line segment, right? Say if you just look at this particular line segment, say it increased by 1.5 times here. Say if it was 3 centimeter, so it became 4.5 centimeter, which means it increased by 1.5, increased by 1.5 times. So similarly, if this is say 4 centimeter, then this will also increase by 1.5 times,
Yes.
right? So it should not be that this is increasing by 3 times and this is increasing by 2 times,
Okay.
right? So this should be 6 centimeters. So that means sides are proportional. Okay, so if you look at the ratio, proportional means the ratio of the sides should be the same. So if you compare the ratio of this side to this side and this side to this side, they should come out to be the same. So 3 upon 4.5 should be equal to 4 upon 6. Okay, so if you are say stretching something, so you should stretch everyone by the same amount.
Yes.
Okay, this is the meaning of similarity. Congruency means if you have this image, you should create an exact copy of this image. No stretching there. Okay. So I mean this is just an activity wherein you have to place a lighted bulb,
Yeah.
right?
So
So
like a shadow, right?
Yeah. So this is the cardboard that you are holding, right? And what this lighted bulb will do, it will create a shadow of this cardboard below, right? And then these two figures would be similar,
Yes.
right? They won't be congruent, because to be congruent, the shadow and the cardboard should coincide,
Yes.
right? But since they are at a distance, so that is why the shadow found will be larger than the cardboard, right? But see, the amount by which you elongate this, say if you elongate this by 1.2 times, same all the sides will be elongated by 1.2 times.
So these sides are proportional.
Yeah, right. And then if you measure the angles, they will be the same. So these four angles, so A will be equal to, angle A will be equal to angle A dash, angle B will be, sorry, this is D, right? D will be equal to D dash, B will be equal to B dash, and C will be equal to C dash. Right, so you can verify both the criteria. So to be similar, both the criteria should be satisfied. So first thing that you checked is sides are proportional. So to check that, what you can do, you can take the ratio of AD and A dash D dash. So you'll get some value,
Yes.
right? And then you again take the value of AB and A dash B dash. They should be the same, right? So AD upon A dash D dash. So this is one ratio, should be equal to AB upon A dash B dash. So this is the first criteria. So this should be satisfied by all the sides. So this BC upon B dash C dash, and then CD upon C dash, and then D dash, right? And then angle A should be equal to angle A dash, right? Angle B should be equal to angle B dash, angle C should be equal to angle C dash, and then angle D should be equal to angle D dash,
Yes.
right? In reality, what we are doing actually, say this is a triangle, right? If I pick this triangle, what am I trying to do? Just elongating it like this, right? We are just elongating it. We are not stretching it like this, right? So this means the triangles are no longer similar, right? So it has to be, so both, all three sides should be stretched. So if you look at this, all three sides are getting stretched, right, by the same amount. But if you look at this, the bottom is being stretched by some amount, but these two are not increasing at the same amount, right? So this is not similarity, this is, okay? Now see, coming back to that quadrilateral that we were looking at. Now can you say whether these are similar or not?
Yes.
Because angles are all equal. So this is the first criteria, angles should be equal. So 85, 85, 70, 70. So we should look at corresponding angles, right? So 85 and then 85, 70 and then 70, 105, 105, 100, 100. Right, then sides 2.1, 4.2. So the ratio is 1:2,
Yes.
right? This is also 1:2. This is also 1:2, and this is also 1:2. So it is satisfying both the criterias, right? And that is why both the triangles are similar. Both the figures are similar. Okay. Now see, this is a polygon, this is another polygon, and if I am drawing one more polygon like this, okay, so say this is similar to this, so we say ABCD is similar to PQRS, right?
Yes.
So remember the sides should be in order. Say if I am writing ABCD, so it is PQRS, okay? And then the second thing is PQRS is similar to, so this is the symbol for similarity, WXYZ, right? Can we say ABCD is similar to WXYZ? Right, so this is, I mean, one important note, right? So if you prove that this is similar to this and this is similar to this, you don't have to prove again that this and this are similar. This is known. Okay.
Yes.
Can you tell me if these two are similar or not?
No, sir.
Why?
Because the first one is a square and the second one is a rectangle.
Yeah, you should not say like that. I mean, see, when you're writing answer, right? So you should write in such a way that you should leverage the definition or whatever you have studied in this chapter, right? So we should not write that this is a square, this is a rectangle, so they are not similar. So see, we can start by saying that two polygon or two figures are said to be similar if, number one, the angles are equal corresponding, and then the sides are proportional, right? So for these two figures, angles are similar or angles are equal. So one criteria is met. Sides are proportional, so you'll say AD upon PS is equal to 1, right? Whereas DC upon SR is not equal to 1. So sides are not proportional. So that is why these two figures are not similar. Okay, so this is what the examiner is expecting from you when you are given such question. Okay, any doubt?
No, sir.
Okay, now tell me if these two are similar or not.
So they are,
Okay, they are similar. Why?
but we don't know the angles of the second one.
Yeah.
We can't see because the first one is a square, so we can say that the angles are all equal to 90 degrees.
Yeah.
But the angles of the second figure is not known.
Okay, so see, first thing is you should not check angles in the same figure. So for example, if you are comparing A with P, so these two should be equal,
Yeah.
right? So see, the first criteria, angle should be equal. So this is clearly 90, right? But is this 90?
No.
So if you draw a perpendicular line, it will look like this, right? So it is an acute angle. So the first criteria itself is not satisfied.
So, sir, is it like if the first is satisfied, then we move to the second?
Yeah. So you have to satisfy both the criteria.
So, the angle is the first criteria always, or the side can be the
You
first
can
criteria?
take any one, because if any one of them is violated, then the triangles are no longer similar, right? So to be quick, you can just write the criteria that is not being satisfied in the very first criteria.
Yes.
Okay. So you can again write the same thing. Two triangles are said to be similar if one, the sides are equal, two, I mean the angles are equal, and two, the sides are proportional. So here you can see the sides are all equal to 90 degree in the first figure. In the second figure, they are not equal to 90.
Yes.
So that is why the first criteria for similarity is not met. So that is why these two figures are not similar. Okay.
Okay. Yeah.
Okay. Now can you tell me the answers for these? All circles are congruent or similar?
Similar.
Yeah, they are not congruent. Right, so they may or may not be congruent.
Yes.
Right?
Yes, sir.
All squares are,
Similar.
yeah, all squares will again also be similar. All dashed triangles are similar.
Equilateral.
Equilateral because isosceles, you can have different angles in isosceles. So this is one isosceles triangle. Say this is, let it be 50, 50, 80, right?
Yeah.
And this can be another isosceles triangle. Say this is 70, this is 70, and this is 40. Both are isosceles triangle, but are they similar? No, right? Two polygons of the same number of sides are similar if A, their corresponding angles are what?
So, one second.
Yeah.
So, the corresponding angles should be equal.
Yeah, corresponding angle should be equal. So this is the first criteria.
And sides should be proportional.
Yeah, sides should be proportional. Right?
Right.
Okay, fine. Give two different examples of pairs of similar figure.
So, similar can be squares and circles, like every single square.
Yeah. So you can take two squares and then two circles. They will always be similar.
Yes.
Non-similar figures.
A square and a triangle and a rectangle and
Yeah.
this.
So ideally you should compare things that have the same sides. So you can compare, say, a square with a quadrilateral. Right, although square is also quadrilateral, but you can take a side which is not regular. Right, and then you can take square and rectangle.
Yes.
Right, I mean you can also take triangle and square as you mentioned, but yeah, it makes sense, more sense to have something that has, I mean, the same number of sides. Right, so that, I mean, you can maybe say, if you have to describe that, the criteria for similarity is 1 and 2. So when you are comparing corresponding angles, so in one case you'll have only 3 angles, in other case you'll have 4 angles. So how will you compare?
Yes.
Right? Okay. State whether the following quadrilaterals are similar or not.
No, they are not.
Yeah. Why?
Because the angles are not equal.
Yeah. And then you know how to, I mean, write this down, right?
Yeah.
Okay. So then we come to, so those were the very basic concepts that we went through. The most important thing here is basic proportionality theorem, right? So this is also known as Thales theorem because this was given by a mathematician known as Thales. Okay, so the idea behind similarity of triangles comes from this BPT, proportionality theorem. Okay, so again, this is the definition of similarity. Uh, two triangles are similar if their corresponding angles are equal, right? Corresponding
Yes.
sides are in the same ratio. So this corresponding is very important. Okay, so when you say a triangle ABC, and then PQR. Right. So you have to compare. So when you say ABC is similar to PQR, right? So you are comparing A with P, B with Q, and C with R, and then AB with PQ, AC with PR, and BC with QR. Right? So then only you say ABC is similar to PQR. Sometimes in the question they give figures like this.
Yes.
So they can make this say PQR. Right? So then, I mean, you compare A with Q, then compare B with P, and then C with R. Right?
Yes.
Then you say A, B, C. Since we are comparing A with Q, so you'll write Q, B with P, so P, and then C with R. So depends on what you are comparing. If these two are same, this and this is same, and this is this and this is same, then you should go in this order. So this is what you mean by corresponding.
Yeah.
Okay. So note that if corresponding angles of two triangles are equal, then they are known as equiangular triangles. Right? So then they are also known as equiangular if their corresponding angles are equal. Right? A famous Greek mathematician Thales gave an important truth relating to two equiangular triangles, which is as follows. The ratio of any two corresponding sides in two equiangular triangles is always the same. So see, I'll give you the triangle which would make it very simple to understand. So say this is one triangle. This is another triangle inside that triangle. Okay?
Sir, your cursor is not visible.
Can you see it now?
Yeah.
I mean, is it visible to you properly?
Yes, sir.
Okay. So you have A, B, C, and then D, E. So ABC is one triangle, right?
Yes.
And ADE is another triangle,
Yeah.
right? So you have these two triangles. So see, this side and this side is parallel, right? Angle A equals to angle A.
Sir, is this midpoint theorem?
Yeah. So this is a generic theorem, but yeah, this can be later used to derive the midpoint theorem as well. Right. So say angle A and angle A is equal in both triangles because it is the common angle. Then you have angle D is equal to angle B, right?
Yes.
Because these two sides are parallel. And then angle C is equal to, sorry, angle A actually should be B. B equals to D. And
Sir,
then, yeah,
I think I should rejoin.
yeah, try rejoining.
Yeah. Sir, am I audible?
Yeah, but your voice is fluctuating a bit. I mean, is it better for you now?
Sir, the screen is not visible.
Let me try resharing it once. But from your voice, what I can understand is there is some network issue at your end. Okay, can you see it now?
Yes, sir.
Okay, is my cursor visible and moving?
Yeah.
Okay. So I was saying we can write A is equal to angle A, B is equal to angle D, and C is equal to angle E,
Yes.
right? So these are the three criterias. So that means these two triangles are similar, right? So now what Thales noticed was that if you take the sides of these two triangles, so say the first triangle is AB upon AD, so this is equal to AE upon AC, AE upon AC, or AC upon EB,
Yes.
and this is equal to BC upon D. Okay. So this is the basic proportionality theorem, and then you can extend this to the midpoint theorem when you say this is the midpoint of EB. So this is for generic, say you can take this line here, you can take this line here, you can take this line anywhere.
Sir,
Yeah.
I actually didn't quite got the proof of this thing when it was done in my school. Like it's something we draw some small triangles and then divide it, right?
Yeah, it is just next, we'll discuss that as well. Now I'm just giving you the premise of this.
Okay.
Okay. So you have AB upon AD, so this is the basic proportionality theorem,
Yes.
right? Other way to write is AD upon DB is equal to AE upon EC is equal to DE upon BC. So this is one more
So
way.
sir, which is the correct way?
So, yeah, I should just eliminate this. Both are correct. Okay. So I should not have written BC upon D because that is one whole side.
Yeah.
Right. So see, this and this is equal to this and this. So I mean you can just prove it. It is very simple. So AB upon ED. So if you just add 1 to both sides. So you have AD upon DB, right? So if you just flip both sides. So you have AD upon DB equals to AE upon EC. So if you flip this side, so you'll get DB upon ED, right?
So we just take the reciprocal.
Yeah. Or let me see, is there any need to do that? AD, yeah, you already have. Yeah, so we should do that. So DB upon AD is equal to EC upon AE, right?
Yeah.
So we have just taken the reciprocal. Now add 1 to both sides. So I'll get DB upon ED plus 1. Will it make any difference if you add 1 to both sides?
No.
No, right?
Sir,
Yeah.
I think I am having some network issues. Like I cannot see your person between.
Okay. That is still an issue.
Yes, sir. Means it just lags for some time and then after 10 seconds, some two or three things pop up at the same time.
Oh. Yeah, is your network stable there?
Yes, sir.
It is. Uh, Let me rejoin once. Okay.
Yes.
Okay. Can you see my screen now, Puneet?
Yes, sir.
Okay.
And sir,
Now, yeah,
if we just had to add one on the on both the sides, then why did we took the reciprocal?
I'll explain that to you. See, why I'm taking reciprocal is, okay, let me just first add and then I'll explain why I did that. So you'll have AD in the denominator, right? Then you'll get DB plus AD,
Yes.
right, equals to EC plus AE upon AE, right?
Yeah.
So you know AD plus DB. So this is AD plus DB is equal to AB, right? So if you add this and this, you'll
Yes.
get AB,
Yes.
right? So AB upon AD is equals to EC plus AE. So AE plus EC is AC, right?
Yes.
So AC upon AE. This is what we were getting here. AB upon AD is equal to AC upon AE, right? Now see, why did I not add 1 here? Why did I take the reciprocal? Because if you add 1 here, so you'll get AD plus DB, which is AB, right?
Yes.
But in the denominator, you'll have DB only. But you don't need DB, you need AD, because AD is a part of the triangle, right? Not DB. So you want to have this in the denominator. That is why you have to take the reciprocal.
And sir, AB upon AD equals AC upon A, and it is equal to BC upon D. This will be given in the question, or we have to assume.
So see, here you have to deal with only these two things for now, as per BPT, right, or basic proportionality theorem, right? So you will be either given AB upon AD, or say you'll be either given any one of this, either this or this,
Okay.
right? So you will be given, say, AD upon DB is equal to AE upon EC. So if this is given, so then you will say D is parallel to BC. Or if you are given D is parallel to BC, then you have to prove, or if you are given D is parallel to BC, then you have to take AD upon DB equals to AE upon EC.
Okay.
Is this clear?
Uh,
Okay, now we'll see how to prove this BPT. So what does this BPT say? If a line is drawn parallel, if a line is drawn parallel to one side of a triangle to intersect the, is my cursor working fine, Puneet, now?
yes, sir.
Okay, if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points. So see, you have a triangle, right? So say you are drawing a line that is parallel to this side. You can have other choices as well. You can draw a line that is parallel to this side, like this, right?
Yes.
Or you can draw a line like this, which is parallel to this side. Any one you can choose. So they have taken this one as an example, right? So if a line is drawn parallel to one side of a triangle, so this line is drawn parallel to one side of a triangle, okay, to intersect
Yes.
the other two sides. So these are the other two sides, right? So this line is parallel to one side and intersecting the other two sides, right?
Yeah.
At distinct points, because these two points are different, so distinct points. The other two sides are divided in the same ratio. So it is talking about the other sides, not the sides to which it is parallel. So it is saying the other two sides are divided in the same ratio, which means AD upon DB is equal to AE upon EC, right? So this is BPT, or basic proportionality theorem, right? So what is given? First of all, what is given?
There's a triangle and D is parallel to BC.
Yeah. So say if the first thing is ABC is a triangle, this is what you know. And then other thing that you know is DE is parallel to BC, right? Then you'll write what needs to be proven or to prove, right? So you
Yes.
have to prove AD upon DB is equal to AE upon EC. Basically, you have to prove the basic proportionality theorem. Okay? Then comes the proof.
Yes.
Now see, the only way in which you can prove this is by taking areas of triangle,
AB.
right? Why I am saying by taking areas of triangle? Because see, you need to include this, 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 right?
Yes.
So one triangle, assume we have not drawn this line so far, but you can
AB.
see one triangle. Yeah, I'm saying this line we have not drawn as of now, right? Maybe we can start from scratch with a bigger triangle. Say this is the triangle, right? A, B, C. What we know till now is what was this? This was D,
Yeah.
right? So far, we know that this and this is parallel, right? Not equal but parallel,
Yes.
right? So to prove that AD upon D is equal to AE upon EC, what we need to do? We need to use triangle logic or areas of triangles. Why I am saying this? Because you need to have this. This is base of some triangle,
Okay.
right? This is again base of some triangle,
Yes.
right? This, you can create a triangle like this. This will be the base of the triangle.
Yeah.
Same for this, you can create a triangle like this and this will be the base, right? Is this
BC
clear?
will be BC will be the base of two triangles. No?
BC. Yeah, but we don't need BC. We need DB and EC,
Yeah.
right? So
Yes.
see, first thing what we do, we draw lines like this to make triangles. So this is the first construction that we do.
Yeah.
This is one triangle that we make. This is another triangle. So see, this triangle, the purpose of this triangle is to find the area of this triangle. Okay? And then you have another triangle. So the purpose of this triangle, I mean, you can interchange anything. So for example, if you look at this triangle, you can take this as base. Or if you take this triangle, you can also take this as base. So depends on whatever, depends on your choice.
Okay.
Okay? Then what else is missing? So area, you got four triangles, right? So one is this triangle for which AD is base. One is again the same triangle for which AE is base. You can switch bases of triangles, right?
Yeah.
Then you have this triangle for which BD is base, and then you have this triangle for which EC is base, right?
Yes.
What else is missing? If you want to calculate area, you have all the bases.
We need height.
Yeah, you need height, which is missing, so you have to construct heights, right? So see, the advantage of using this figure is that if I draw one height like this,
Yeah.
okay, so this makes 90 degrees. So this is a height for this triangle, right, as well as for this triangle, right? Is this visible? For example, if I extend this triangle, if I look at this triangle, right, this triangle looks like this. It is a bit tilted. So this is one side, this is another side, and then this is the third side, right? Now what I have done, I extend this side and draw a line perpendicular. Is this also the height of this triangle? Right, because height of such triangles will be external, right? So you can have two different types of heights. So one is internal. So for example, if you take this triangle, this is an internal height, right? If you take triangles like this,
Yes.
can you draw the height inside the triangle?
Yes.
How can you draw that? Say this is the base and you have to draw the height.
Oh, okay. No, we cannot.
So you have to draw it externally like this. So this will be the height of the triangle, right?
So, but if that side is not the part of a triangle, then how can we say it is the height of it?
So see, height means distance of one end to the other, right? So
But
this
it's
distance
not
should be,
inside it, right?
yeah, so you are measuring this distance only, perpendicular distance between these 2 points. So what is height? Height is the distance between 2 points, the perpendicular distance between 2 points, right? So you are not saying this is a part of the triangle, this is just an altitude. Altitude is basically meant to say that this is the perpendicular distance between 2 points. It can be either inside or outside the triangle. Okay, any doubt?
Yes.
Fine. So we'll use common names, what they have given. En. Right, so for now I'll just erase this one to avoid confusion. Okay, so this is now erased. Now this seems more clear. Now see, this is one triangle, this is the base and this is the height. This is another triangle, this is the base and this is the height, right? So you can write area of, say, triangle EDA, right? What is the area of triangle EDA?
Half into D. So, half into DE into N.
Half times D,
E times N.
D times, so see, half times base times height is the area, right?
Okay. Yeah. So, half times DA times N.
Yeah. So half into dA,
So,
yeah.
I always get confused in like which side is the base.
So see, base is the side in which you drop the altitude. If you drop the altitude like this will be the base. Right? If you drop the altitude like this will be the base. So base can be anything. So it depends on you, what you are using as altitude. right? It is not that this is the base of the triangle. So it would depend. So see, area of triangle, so if this is ABC, right? So if you are dropping altitude, if you know this height, so you'll write half times h times BC, right? If you know this height, say this is h1, so you'll write half times h1 times AC, right? If you know this height, you'll write half times h2 times AB. So base was changed based on what you choose as height.
Yeah.
Okay,
Okay.
is this clear?
Yes, sir.
So this will be half times dA times En, right? So this is the area of the first triangle. So why did we calculate the area of this first triangle? The purpose is to get something like AD, which is here.
So that we cancel it out.
Yeah, right?
Yeah.
Then you calculate area of this bottom triangle, right? This will be area of triangle. What is that triangle?
So which one?
This bottom triangle.
BDE.
It is triangle BDE. This will be half times, what is the base here?
BC.
What is the base?
BC.
B. So see, this is the triangle BDE.
Yeah, yeah. So DE, right?
DE.
Yes.
Okay, first of all, look at the altitude. What is the altitude?
So we don't have the altitude.
So see, this is the triangle,
Yeah.
and then we have drawn this as an altitude which is 90 degree to this line.
Okay. So we take any as the height.
Yeah, En, right?
Yes.
En is the altitude, right? You understand that this is an altitude to this triangle as well,
Yeah.
right? Because this is slightly tilted, it won't be possible to draw a line inside this, right? So to compute the distance between this and this point, we have to draw a line outside which is perpendicular to this, right? So what we did, we just extended this like this, just like we did here. We just extend this like this and then compute the perpendicular distance. Same thing we are doing here. So we are extending this and then computing the parallel perpendicular distance. Okay?
So sir, if the triangle is like BDE and we take the height as EN,
Yeah.
so aren't we calculating the area for BNE?
Bn?
E.
No. No, it is not the case. So see, when you are calculating the area of BNE, the base will be Bn. Here you'll take base as BD only. Okay, is this clear?
Yeah.
So here, since the altitude is in this direction, so this is the base,
Yes.
right? So BD is the base.
Okay.
By doing so, you got AD and DB, right?
Yes.
So the ratio of these two, if you take the ratio of these two, area of EDA upon area of BDE, this is equal to AE upon EC, right?
Yeah.
This is the first thing. Now the second thing. Again, you have to repeat this exercise for the other half.
Yes.
Right, now I'll erase this. Now see, we got these two. We have to get this two as well, AE and EC. So one triangle you already have, right? So this triangle you already have. Then you create one more triangle like this, right? We can do this.
Yes.
Okay. Then what is the next step?
So now we calculate the area for AED, right?
Yeah. So area of AED is equal to half into what is the base?
AE,
A. What is the height?
DM.
Yeah, you have to draw that height, right? First.
Yeah.
So when A is the base, the height will go like this, right? Any question, Puneet? Puneet, sorry, I just got disconnected. Don't know why.
Yes.
Okay. Uh, so we have to calculate area of triangle AED, right?
Yes.
So this was AED. So we drew a perpendicular. So because we already named it N, we'll name it M,
Yeah.
right? So half times AE times AM, DM, right?
Yes.
So this is the area of triangle AED. Similarly, to have EC, we'll compute the area of triangle ECD, right?
So is it necessary to add ACD, or we can take anything like DEC?
B,
EC.
yeah, so see, if you take BEC, right? So if you take this triangle,
Sir,
yeah,
DEC.
okay, DEC, yeah, okay, so you're saying about this order, yeah, you can name it anything. So you can name it until and unless it forms a proper triangle. So ECD, DEC, or EDC, you can name it anything,
Okay.
right? So this will be half times, what is your base here?
DE, right?
DE. So see again, what is the perpendicular? First of all, let us see the perpendicular,
DM is the perpendicular.
DM. So DM is falling into which line?
CM.
C?
CM.
Yeah, but you have to restrict yourself to this triangle,
Okay.
right?
CM.
So you'll write half times C, because if you go till M, then you'll calculate the area of this triangle.
Yes.
So half into C times dm, right?
Yeah.
Now again, if you take the ratio area of AED upon area of ECD, this will be equal to AE times C,
Yeah.
right?
Yes.
EDA. From here, what did we get? EDA upon BDE. So this will be DA upon BD, right? Right, so we made a mistake here. So this should be, I mean, did you get what I'm trying to say? This should be DA upon BD, right?
Yes. And everything else would be cancelled.
Yeah. This will be DA upon BD. Okay. And then from here, area of ACD upon area of ECD is equal to AE upon C.
Yes.
Right. Okay, this is B. Right, because this is
So it should be ACD.
AED, right?
Yeah.
So this is AED. Okay. So this is AED here and ECD here. Right.
Yes.
So EDA and AED is the same, right?
Yeah.
And BDE and ECD. So what is this? Is BDE, right? So for BDE, you have to again reconstruct this triangle. So this was BDE, right?
Yes.
So BDE and DCE. So these are two triangles, right? So see, this triangle, if you notice, it has a common base, right? Both the triangle. So one triangle is this, the other triangle is this. They have the common base and they are between the same parallel. So this is one parallel, this is another parallel, right?
Yes.
So you know this theorem, when two triangles lie in the same base and between the same parallel, what property they satisfy?
They are congruent.
No, they are not congruent, they have the same area.
Okay. Yeah.
Okay, I'll show you the proof as well. So see, that means the area of BDE and area of ECD are the same,
Okay.
right?
Yeah. So it means dA upon BA should be equal to A upon C.
Yeah. So dA upon BD is equal to AE upon C. So this is the proof of DPT. Okay, is this clear?
Yes, sir.
Now see, the theorem which says triangles that lie between the same base. So this is one base, right? So say you have one triangle like this. And let me draw one parallel line like this. And then you have another triangle like this. Okay, so these are two triangles, right?
Now I, yes, sir.
A, B, C, D. Right, now what the theorem says, the triangles have a common base, right? And they
Yes.
lie between the same parallel. So they lie between the same two parallel lines, right? Theorem says they have the same area. right? So when they lie between the same parallel, if you draw a perpendicular line like this,
Yeah.
so this is an altitude of this triangle, say n,
Yes.
and
Yes.
then this is the altitude of this triangle, right?
Yes.
So is AM and DN equal?
Yeah.
Because these two are parallel lines, so between parallel lines distance should remain same no matter where you measure,
Yes. Yes.
right? So area of the first triangle would be half times BC times AM. Area of the second triangle would be half times BC times DN,
Yeah.
right? So AM and DN are equal, so the area is the same.
Okay.
So whenever you see triangles that have the same base and between the same parallel, so now you understand, right? This is the base because this
Yes.
was the height. Now instead of that, if I take this as height, so although this may look like base, right? This looks like
Yes.
it is the base of the triangle, but it is not the case. Depends on what you are taking height. Okay, so if you
So the
take,
height,
yeah, go ahead.
the height should always be perpendicular on the base.
Yeah, right. So
Okay.
say if the height starts from this vertex, base is opposite to this, right?
Yes.
You know the concept of trigonometry, right? Wherein it, base and perpendicular changes based on the angle and angle of interest. If this is the angle of interest, this is the base and this is perpendicular. If this is the angle of interest, this is the base and this is perpendicular.
Yeah.
So you don't have a fixed base, and this is not the literal meaning of base. Base means you choose a height, say if this is the height, this becomes the base.
Yes.
Okay? So try to think like this. So what is a triangle? So how do you derive the area of triangle? Like this. So you divide a parallelogram into two parts, right?
Yes.
So if you consider a rectangle, it will be length into breadth, where length is the perpendicular height, right? Like this.
Sir, can you repeat?
So area of a rectangle is, so if you take a rectangle, it is length into breadth, right?
Yes.
Where length is the perpendicular distance, right? So basically the height.
Yes.
Similarly, if you look at a triangle, so you should look at the perpendicular distance. So this will act as the length, and you don't multiply the length with this, or say if you take this as the length. So this is your length. Now you will not take the same thing as your breadth. What will be your breadth? This thing.
Yes.
The thing that is perpendicular to length, right?
Yeah.
Will be your breadth. So similarly here, you are drawing a perpendicular to this, so this automatically becomes your base of the triangle, and this becomes the height.
Yes.
Okay, is this clear?
Yes.
Is this derivation clear to you? This is very important. I mean, you can get a direct question on this derivation.
Okay. Yeah.
Okay, now I guess you'll be able to prove it on your own.
Yes.
Try doing it on your own once. Okay.
Sir, this BPT and the questions on that modulus, I will revise it before tomorrow's class and tell you if I am having any doubts.
Yeah, sure. Okay.
Yes.
Then we'll connect tomorrow.
Yes.
Okay. Fine. Bye.
Bye, sir. Thank you.